Hello, everyone. It is time for the next lesson in grade 11 physics online, university level. Here we go. Uniform acceleration questions. Continued, we're going to look at type 2, I'm going to call it, a different combination. So it's going to be type 2 and an equation intro. So I'll just squeeze that in there. So type 2 and equations intro. There's a bunch of them. So yeah, here we go. Let's do a little review of type 1 of what we've covered so far. So we have a car uniformly increasing its speed from 6 meters per second to 30 meters per second in 4 seconds. I want you to determine the acceleration and the displacement during the 4-second interval that takes. So I'd recommend you press pause and give it a try and see if what you do matches what I do once you press play. All right. So, hey, thanks for pressing play and let's do this. So here we go. So I'm going to do a VT graph, of course. We're using the VT graph method for now. And so here we go, VT graph. We're starting with a velocity of 6 and ending up at 30. So V1 equals 6, V2 equals 30. And it takes 4 seconds to make that change because we are told that it is uniformly increasing its uniform acceleration, uniformly increasing its velocity. We're going to go from start to finish with a nice straight line. Otherwise, we'd have curves there and we'd need calculus to calculate things, especially the displacement. And so here we go. We've got that. And so let's just look at acceleration. So that's I already picked out the given information from the paragraph there. So we can go ahead and do acceleration equals delta V over delta T. You can calculate delta V first if you want separately, or do it right in here as V2 minus V1 over delta T. And so it is 30 minus the 6 over the time of 4. And so we're getting 24 divided by 4. And 6 times 4 is 24. So we're getting 6 meters per second squared is the rate of the acceleration. And so that's cool. Therefore, statement at the end saying therefore the acceleration, because this is a vector, really it's understood that forward is positive. And so, it's not really focused on a ton here. But in the end, the fact that this is positive means that it's forward. So, technically, to have a vector listed, you really should have a size, right? Because it's a vector, we should have a size and a direction, right? Quite often, the way they're worded, it's not super focused on, and so I can see that being missed once in a while in the answer. But try to include it, please. Okay. All right. So that's that part, and then the displacement. We're just going to say, oh, and by the way, doing this from the graph, we know the idea that we're talking about slope, right? Equals acceleration, and so equals rise over run, right? It's not something we really need to worry about, but I mean, it's just nice to sort of mention that it's there as a physical concept, because we're using the physical concept of area, right, to get displacement. So area here is going to be a rectangle and a triangle. You can see them, right here and right here. There's your rectangle and your triangle. And so we've got a very easy, guide to pick out the numbers. The length times the width of the rectangle is the 4 times the 6. And then 1/2 of the base of the triangle is also 4. And the height is from 6 to 30. So that would be the 24. Right? And so if I'm doing the numbers here, I might simplify my life a little bit and divide that in, get a 2. 2 times 24 is 48. This is 24. And we'd have 60 and then the 12, so 72, I'd say, right? delta D equals 72 meters. And again, same idea. We have positive and forward. Therefore, and so on. Okay, so there's that previous work all itemized out for us here. Hopefully that's making sense. And I'm just going to group these a bit, make them stand out as two separate things, right? All right, just hang on one quick second here. All right, so this, I'm going to start to introduce the uniform acceleration equations. So I'm going to show you them, but I do not want you to just start using them exclusively. Certainly not yet, maybe not ever. So you're going to need for this course, the way I'm doing it, for you to be able to work both ways. So VT graph and the fancy equations. And so these are little memories for me here. Just one second, please. All right, I'm back. I was talking with a staff member. I think I was about to tell you, a personal story for me from my life. Two examples, two situations where I let myself down. I let the people around me down. Like, hey, you're a physics person. You should be able to calculate this. And I wasn't able to, and it bugged me. And then so later on in my teaching, this VT graph method that I've really gone with makes it so you could answer the question someone wants to know. And so one situation was back in high school, Sault Ste. Marie. It would have been 91 or 92. And there was a bridge walk. And the Mackinac Island Bridge goes between the upper and lower peninsulas of Michigan here. So it's a bridge right in there. If you ever have a chance to go, it's a very, very big, like, I don't know if it's like world's largest. It's not world's largest, but it's a very big suspension bridge. So they might have northern USA's longest or whatever. Anyway, so it was a bridge walk, and it was just a neat event. And also I went with a bunch of friends. And so some people in the class, we brought like some pebbles, to drop off the bridge so we could like time how long the pebble took to go to the water. And so then the idea was to like calculate the height of the bridge based on a measurement, right? Because we were in physics, we knew what we were doing. And so like 3 of us from the physics class, and then our other friends that were there with us thinking, oh, this is cool, they're gonna be able to measure this, or they're thinking we're a bunch of nerds, whichever it was. And okay, I'm okay with my life. So the disappointing thing was we couldn't remember the fancy equations, right? So here's some fancy equations that are to do with this. And so I think the equation we needed was like delta D equals V1 delta T plus 1/2 acceleration delta T squared. We couldn't remember that one. So we would have had the initial velocity was 0. The acceleration due to gravity is known, the time we can measure it, and so the displacement we'd be able to calculate it. Okay, but we couldn't remember the equations, so we weren't able to calculate it. Then fast forward to another point in my life in Malign Canyon out west, when I was out with my future wife at the time and another colleague. We were on a road trip. So we're at Malign Canyon, and the colleague, who was actually just the person who was in here talking with, actually we've been working together for quite a while. I started teaching in '99, so So anyways, it's been a while. So she said, "Oh, I just wonder how high up this is." And so I'm like, "Eureka!" So I literally drew a VT graph in the sand to help myself do the calculation, and calculated based on the time of dropping a stone how high it was. And she was like super impressed, right? So I could fake the story and say that it was my future wife that she was so impressed she ended up marrying me, but it was the other staff member that I was. Anyways, so yeah, the idea is the VT graph. I don't want you to abandon it, right? So I want you to see the equations, appreciate the fact that they're kind of obscure, like they're like, okay, where the heck are those from? In the long run, they're a little hard to keep memorized, and so a VT graph is going to be really, really handy going forward, even once you get good with the equations. So VT graphs are also a lot more intuitive and help you visualize what's going on. So later on, we're going to look at a question where it's like, we're slowing down, and then it's like, well, what if we kept slowing down and we went all the way to a stop? You can extend the graph. Or what if we ended up going backwards? So you can extend the graph and really visualize the different portions of the motion. And a lot of times you can use that graph to help you work with the equations if needed, just to help you visualize what's going on. All right. So full disclosure though, there are some tricky examples like type 8 that I'm going to get to later on where the equations are amazing. So you just use them, right? And what it does is it makes it so that you don't have to work as or be able to work with quadratics. So like if you don't, you'd have to use substitution elimination for a linear system, and you'd have to use quadratics. So the equations kind of do that for you and make it so you can get answers more easily. Okay, but in a certain situation, you're definitely going to want to use them. All right, so I'm going to clear my throat just 1 second here. All right, here we go. So these are the equations. You have these 5 uniform acceleration equations, and we're going to get to know them as we go through this. I'm not going to do anything with them at this point. But yeah, those are what we're going to be using. So let's look at the type 1 question that I've already done with the BT-graph method, what that would look like with equations. All right, so for acceleration, you're going to find that it's really the exact same process, right? So for acceleration, you're going to look at the method for this. I should have pointed this out a little bit more, right? The idea is this is my baby here, my uniform acceleration equation selection matrix. I've coined the term UASM, and it caught on here at my local school, at least anyways. People are like, oh, UASMs are the best. And so last year, my daughter was taking an online physics. No, friends of hers the next semester were taking online physics, and so they were struggling. And then she showed this. She got this from me, of course, because I was helping her through a course. And so then she shared that with the rest of the students, and all of a sudden they're able to do these questions much better. They weren't shown that in their course that they were doing. Anyways, so the idea is you circle the ones you have or you're looking for, right? And so if you have all 4 of them, you have or looking for, I should say, all 4 of them, you're going to have 3, and you're looking for the 4th, then you can use the equation, right? So in this case, we have let me just jump to here. We have v1, v2, time, and we're looking for acceleration. So it's a little hard to see here, but that's v1 and v2, or v initial and v final, right? The delta t, and we're looking for acceleration. So you can tell we're able to use that equation, or if it's easier in the video to make sure to know what I'm talking about here, it's these ones, right? So we're going to use that equation. We're just going to say acceleration equals delta, or v2 minus v1, right? So v2 minus v1 over delta t. And obviously this is the same as using the slope method, right? So this is the same as the slope method. Nothing different so far. And it's, of course, the same as the acceleration equation that we already know, right? So basically, when you see this uniform acceleration equation selection matrix, or the UASM, basically you're like, I already know this one. So we've already done this one. Already know this one. Right? So there's really only 4 new ones, but they're complicated enough that they're not super easy to just get memorized and so on. So here we go. Obviously, this is the same stuff, right? You're just going to have v2 minus v1. You're going to have the 30 take away the 6 over the 4, and you're going to get the 24 over the 4, and we're going to say, hey, there's that 6 meters per second squared, confirmed that we already knew. Same deals as well for positive and forward and so on. And there's really absolutely nothing different at all for that. Okay, even though we're doing this fancy new with equations method. Okay, that's the case for acceleration. It's really the same. Displacement is substantially different, though. Well, yeah, it's the way it feels like you're going about it feels different, at least. So let's look at the selection matrix here. And by the way, if I was selecting for the work there, I'm just going to point out that I would have circled the v1, v2, acceleration, and so on. And you can see there's only one equation where we have all 4, and that's why we picked that equation, right? So let's let's get rid of that. And so now we're going to say, okay, well, we're going to use the given information, right? So let's start over here. We have, actually, I should have just gotten rid of the acceleration part, because we're not talking about acceleration this time. We're just doing the we're looking for displacement, right? Now you look at the displacement equation and you're like, oh, okay, so I can use this equation, right? So focused on, in the question, we have v1, right? v1, v2, time, and displacement. And so if I change those all to be red, it'd be like, hey, there's the one, right? We have all four. And so we're working with all four, at least anyways, right? So we can write that one down. We can say, okay, well, we've got this equation, delta D equals V1 plus V2 divided by 2 times delta T, okay? And we're gonna talk soon about like what it means, why it makes sense. But for now, let's just see that it works, okay? So we're gonna put in V1 and V2. So we're gonna have 6 plus 30 over 2 times the 4. And let's just do a quick little check, right? Does that look the same as what we did here? 4 times 6 plus 1/2 of 4 times 24. It looks quite a bit different, doesn't it? And there's a reason for that, but they both make sense. And I'll be able to justify that for you. But let's just see what we get. So we have the 36 divided by 2 times the 4. And so I'll just run the numbers on a calculator to make it easy, right? 36 divided by 2 gives you the 18, and then times the 4. And hey, look at that, 72, same as last time, right? So 72 meters and plus and forward just like before, and therefore just like before, and so on. But it looks like a bit of a different process, but this is obviously the same as, this is the same result. Okay, so both of those are same results before. This one, obviously, because we did the exact same thing. This one, we did kind of different stuff, but it gave the right answer. Okay, so the equation method worked. And so, going forward, the next steps, gaining trust in the equations is one thing we're doing here. And then also, of course, we're going to gradually gain an understanding of why they work, what they actually mean. Yeah, so I might mention that one a little bit more. So why does this work? Why and how, right? So what does it mean? Why, how does that make sense? Our graph, if we look at it, we had a 6 to a 30 and a 4, right? And so the VT graph method was this one, right? So the VT graph method was triangle and, sorry, just botching the picture here because I'm going off script a little bit here. Just kidding, I don't have scripts in front of me. So it was like this, right? So that was the delta D equals rectangle plus triangle. Yeah, rectangle plus triangle. And then this one, if you notice, we're looking at the average, right? This is like the average, or like the middle of these two. And so can you see why the average times 4 is going to give you that same answer in the end, depending on how split things are in the middle? I think it should start to make sense here, right? See how this triangle, instead of being here, is sort of abstractly put here, the way we're talking about it. So basically, this equation is really just saying, well, if you had the average velocity, since you have uniform acceleration, if you have the average velocity times the time interval, you get the displacement. That's really what that one's about. But pictorially, it makes sense as well, where this would be equal to the big rectangular box where it's the average, right? So it really does make sense. That equation is not that hard to sort of understand and respect and get what it means and why it works. Okay, it just sort of seemed weird first time looking at it, maybe, but then you look at it, hopefully you're thinking, oh, okay, see how the VT graph idea and understanding is helping us understand that thing makes sense. Okay. Type 2. We're on to type 2. So we're going to give you the initial velocity. We're not going to give you the final velocity anymore. You're going to have acceleration instead and time. Okay, so VT graph method. Let's do it. So you're going to draw a 20. Notice how these are in the same direction here. So we've got a positive and a positive. So you can tell that it's speeding up. That's why it was important for us to have that like direction of acceleration lesson and so on. And so it's going to be speeding up. So we're going to have a picture like that, right? And then, so you have the 6 labeled, the 20 labeled. We just needed to recognize that we're speeding up. So that allowed us to make that VT graph. And so at this point, we can do the slope. We can work with slope information or displacement information, like slope or area, basically information at the start, right? So for this one, I'm going to emphasize that a bit more. As I've been doing this more and more, I update slides a bit, but I mean, so the idea of this, when you're trying to focus on like, what do you do next? Let's emphasize before, picture this question being like this, where it's like, I'm going to work with slope or area, right? And of course, when I say that, really we're saying, well, are we working with acceleration or are we working with displacement, right? I'll just jot those in underneath handwritten here. So acceleration or displacement. And so what happens in this case is, like, this is really a where to start, right? I should probably write that better. Let's see if, yeah, that's not what I was writing. So the question, this is about me helping you see like where to start, right? That's the hard part with these questions. You have this question and you're just staring at it and thinking like, what do I do? How do I get started on this, right? And so the big thing that I'm going to be emphasizing all the time, lots here for us, is that you're going to use what you have to work with, right? So, in this question here, should we start working with slope, which is acceleration, like, or area and displacement? Well, you have this, right? So since you have, right, data, information, or whatever about acceleration, then that's going to make this a really attractive thing to start with. Okay, so that's why in my next box that I had sequenced here for myself to show, you're going to say like, okay, well, we're going to use acceleration because we have that number. So we can put that number in, right? The 5 acceleration can go in, V2 and V1 can go in, right? And so on. Right? So it's always going to come down to, you're going to work with slope or displacement, and which one you work with is really just depending on which one you have and you can use, right? So numbers are plugged in, multiplying both sides by 6 gives you 30 equals, right? That stuff, and then add 20 to both sides. We're going to get our final velocity of 50. So as predicted, we've sped up because our acceleration is in the same direction as our velocity. All right. So that's the slope stuff. And then after that, you're thinking, okay, well, now let's work with displacement, because those are our 2 main concepts we're gonna go through all the time, right? And so we're gonna look at the area here. So we have obviously a rectangle and a triangle as normal, right? And so we're gonna look at those values, put some numbers in. We have the 20 times the 6, great. We have 1/2 of the base, 6. Then we have the delta V. Well, the delta V in this case is a little weird, right? Because we don't really have that number. Well, we do now, I guess, because of the 50, right? But you can tell we wouldn't have been able to start with it, right? So that's when you can say, okay, well, delta V in this case would just be the 20. What am I doing there? Yeah, so I have here. So 30. Yeah, so basically, this is what I want to focus on for now. I have ignore the green stuff for now. But we have the 30 there, and so it's 1/2 of 6 is 3. 3 times 30 is 90. Okay. The green is there to help us understand the equations. So I should have little boxes over those right now, so you're not like distracted by them. I distracted myself with them. So let's leave it like that for now. Okay. So I want to just point something out that you have to watch for. Delta V, of course, is a positive in this case, so it's good to go. There's going to be times where we have to worry about it being a negative. But the bigger thing I want to watch for here is a common mistake that people do, that they think that delta V equals delta D over delta T. Okay, and it comes in this question here where it's like, trying to figure out what's what, right? So that is not true. That's not a valid equation. The change in velocity is not delta D over delta T. The average velocity is delta V over delta T, right? So if you did this and you said, okay, 30 delta V, right? And you just calculated this out, that you're trying to get displacement but the wrong way. So instead of doing the right stuff here and getting 210, sometimes people say, oh, delta V equals this, and it gives us an answer of 180, and that's not true. Correct answer is 210, right? So that's just something to watch for. So I just wanted to show that, okay? The 210 you would get by doing the average, right? That middle number. Sorry, the delta V is the 30, but I mean, yeah, if we did the actual average, it might have would have been all right. So the correct way of doing this is over here where we say the average velocity, right? And so the picture to do with that one is, well, the correct answer is 210, of course, right? And then the picture would be the average, which would be 35, okay? So the average is 35, giving us the correct value. So this slide is absolutely focused on trying to get you not to ever do this, right? Notice that you'd be off track if you're doing this because you're not you're not saying, oh, it's displacement and so it's a rectangle and a triangle, right? So please follow along with what I'm trying to show you, right? So next step here, obviously the acceleration stuff is the exact same, okay? So acceleration stuff, you would have circled what here? We would have circled the accelerations. So that's the accelerations, I think. Pardon me. The times and the V1 and the, what else did we have? I have to go back to the original equation here, original thing. I guess we're looking for V2, right? Yeah, that's what it is. We're looking for V2, right? So obviously we pick that equation and do the same work as normal. I'm kind of burning past that one because it's already done. The new one that we're going to focus on more thoroughly here is we have to figure out what we're going to do for displacement, right? So for displacement, we're going to circle that one. There's your displacement. We are given V1. Yeah, we're given V1. And again, I can go to the page where this is bigger and easier to see, but just trust me, that's V1. This is displacement. There, now it's obvious. The accelerations, right? And we want, and also the time, right? Yeah, we were given the time also. So you can tell that in this case, we have, what did I do there? Oh, I circled one by accident. I was going to say, we're not using that equation, right? That's not there's not an X there. There isn't a delta T in the bottom equation. So what we have is this equation works. Okay, so go back to the easier to see ones here and picture doing delta D and V delta T's. And what else did I have? The E1s. I apologize, I'm off track here. V1, V2, acceleration, the bottom one. There we go. So first two and last two, I'll just do it that way so it's easier to get here. So first two and last two is what we have and are working with. And so this is the equation that I'm going to show you. And I'm also going to help justify why that one makes sense. Why is delta D equal to V1 delta T plus 1/2 acceleration delta T squared? Kind of a fancy, sounding thing, right? So there it is. There's the equation. And let's just see that it works. Put in V1 and delta T and 1/2 of acceleration, and this thing's squared. Notice that calculation-wise, I should put an extra line in here for us because bed mass is important. So let's get that itemized out. So the calculations here would absolutely have to be, the 20 times the 6 can go ahead and happen at this point. And then, I'm just going to keep all of this stuff here and show that this had to be 36, right? This has to be done. Bed mass, brackets, exponents, and so on, right? How's it going? Yeah, of course. Yeah, no worries. I'm doing a video for my online class in case you're wondering if it feels like I'm talking to myself here, right? A student just giving the serpent a pencil, that's all. So bed mass calculations, it gives you the 210, gives you the correct answer, right? And so let's just compare to the area calculations that made a lot of sense to us. If you look at what things are here, the 6 is the time, and then the delta V is, delta V, I'm going to show this one next here. We know acceleration equals delta V over delta T. And so delta V is really acceleration times delta T. So that's why I have this written in here as acceleration times delta T. So as a result, then, we end up with, right, acceleration times delta T is the acceleration delta T squared stuff, right? So that's what it's coming from. That's why it works, right? It's just substituting. It's really substitution elimination, right? Substituting one equation into another. The VT, delta V over delta T for acceleration equation gets substituted into the area concept, builds the equation. That's where they're from. That's what those equations are. They're just combined for you to make your life easier, right? All right, so let's continue on here and just pause for one quick second. All right, type 2 slowing down case, and let's just do this. So we're getting a little long in the video, so I might show the version that sort of worked out and walk us through it, okay? Obviously, we have that we're slowing down. I just think I changed my mind. I better do this carefully here, right? Again, same deal. We've got, positive and negative, so you can tell it is slowing down. And we're going forward, but accelerating backwards. So technically, you could call it deceleration. Deceleration isn't always the case for negative acceleration, but it is in this case. So there's nothing wrong with that. So we're starting at 20. Give yourself some room to slow down to some final V2. That's my V1. Here's my VT graph. There's my 1.4 seconds. And so we're starting with this velocity and going with uniform acceleration to that one, right? So make that be a nice straight line. I'll fix that up, make it better, right? So I've got my VT graph. Great. So if I'm looking at what I'm going to work with here, right? So is it acceleration or is it displacement that's going to be handy for us to work with? Well, you can tell you've got acceleration, and so you're going to use it, right? So acceleration equals delta V over delta T. And so we're going to be able to start putting values into that nice and easily. So acceleration equals V2 minus V1, obviously also. And so we have our acceleration of -5. We have our V2 that we're wondering about, minus V1, which is 20, over time, which is 1.4, and so on. Right? So we got this new case where we're slowing down, and we have some algebra to work out here. So let's do it. Let's multiply both sides by 1.4. That gets rid of that. Divide by 1.4. We're going to have 5 times 1.4. Just remember that's negative. 5 times 1.4 gives us a 7. All right, so this is a -7 over here. Equals V2 minus 20. And then we're going to add 20 to both sides. And end up with, come on in, V2 equals 13 meters per second, forward and so on, right? We just pause quick here, one sec. All right, so the initial velocity of 20 slowed down to 13. Life's making sense. And then if we were to look at the displacement for this, so we got the acceleration already. I have a note there about if we went backwards longer, but let's just, we can might as well mention that now. If we went back for even longer, of course, it would end up with like a negative velocity, and the area analysis would be even sort of trickier. But I think we can go ahead and do displacement here and look at the rectangle plus the triangle. And we have, in this case, now that we have the information from the initial one, we could go ahead and do that. Because we're doing the VT graph method, we have to. I was thinking of the equation method. So we're going to use the new information. So this is like calculated, right? So I'm going to point out that we're using that thing. Right there. I'll make sure I get this right. It's hard for me when I've paused and come back. times the 1.4, and then plus the 1/2 of the base times the height of the triangle. Now, the height of the triangle, this is one of those ones where we have to not put it in as a negative. The delta V is -7, obviously here, right? If you look at it, it's gone from down to 13, so it's a delta V really equals -7 in reality. But in your work here, when you're looking at like the height of the triangle, we're not going to put it as a -7, right? So this is going to be like the height of the triangle. So it equals 7, not -7. So we put it in as a 7 and we can calculate stuff out. So we're going to have 13 times the 1.4 gives us 18.2 plus the half of 1.4 and 7. So 0.5 times the 1.4 times the 7, or if you wanted to like have less button strokes, you could have done 3.5 times 1.4. Get 4.9. In case you don't believe me on that one, 3.5 times the 1.4. Right, we'll give that same number. Right, the half can go into the 7 easily, becoming a 3.5, and so on. Little math tricks are good to know that they make sense at least, anyways. So we need to add that up. We got a 4.9 and an 18.2, so plus 18.2. Darn it, what did I do? 4.9 plus 18.2. All right, 23.1 meters. And again, you can tell it's a plus here, so it's meaning forward, right? Therefore, your statement would be to do with that and statement to do with this. I don't know why I'm still writing in green, but survivable, right? So that is the method for that. This is just the last time I calculated it out. Same kind of work. I just wanted to make sure I was emphasizing the idea of picking, working with acceleration because we have it, and so on. So I'll do that one out. Instead of going through it and trying to make sense of it, I just figured it easier to do it step by step with you, make sure it makes sense. All right. So in the equation method, I'm going to do delta D first because we can, whereas you can't in this one. So it's kind of just showing some of the power that's in the equations, right? So we've got V1s, and we've got acceleration, and we've got delta T. All the x's circled, all the, circling the ones where it's in there, and then we're looking for displacement. Okay, so which one has all 4, and we can use it right here, right? All 4, use that sucker. So V1 delta D plus 1/2 acceleration delta T squared. No, same one again because obviously we're doing a type 2 question still. And so yeah, you can just fire the numbers in. The V1 can go in as 20, the time can go in as 1.4, the acceleration goes in as -5, and so on. And like full on, just put them in as the values are. -5 goes in, okay? Has to go in. And so we end up with this answer, 23.1. Imagine that, same stuff, okay? And again, the average idea here still makes sense in terms of how that, actually not that one's not the average one. So I guess I just got to leave that one as is. Just say, hey, it works. We know it's good. Because we know we justified that this term makes sense, right? For V2, it's just the same as before, right? So I just calculated delta V first and then delta V2, but it's the same kind of stuff. Just 1 sec here. All right, so life is making sense. The equation method and the VT graph method producing the same results as they should always, right? So let's just extend our knowledge and our ability to tackle new things even farther. What about like how long it takes to slow down and stop? Well, from the VT graph method, I showed this a little bit earlier in the video. We extend the graph to to exactly there. The acceleration stuff, easy peasy. You just go like normal. This is the next stuff, right? Yeah. So displacement, The delta t work would be the same calculations, right? So I'm just glossing over that. Displacement, we could do area under the graph, right? So let's do that quick. So delta d equals just a triangle in this case, right? And so it's 1/2 of the base, which would be the 4. That would be the 4 that we figured out from there. So 1/2 of the base times the height of the 20. And so that's going to give us 1/2. 4 is 2, 2 times 4 is 4, 2 times 20 is 40. So it's 40 meters. And again, it's positive, so it's forward and so on, right? Therefore, blah, blah, blah. Okay. If we're doing the equation work, right? So this is from the equations. Then what would we pick out? I suspect it's probably that same one we used last time, right? So we have V1, and we have acceleration, and we have V2, and we want displacement. Is that right? Yeah, this is, I feel like I'm picking the wrong one here, but so, time, we already did, displacement, V1, V2. This isn't really a type 2 anymore, is it? Back to being a type 1, I guess? Yeah, it's back to being a type 1. But if we were going to do displacement first here, we could do that. We'd pick this equation. So that is a V2 squared equals V1 squared plus twice acceleration delta D. I feel weird that I'm doing this one because I feel like I shouldn't be yet. But V2 is the 0. V1 is the 20. And twice acceleration. So acceleration was as a -5, and displacement is what we're looking for. So let's see what we get. Let's do 20 squared, gives you 400. We have the -10 from there, delta D. And so we take away 400 from both sides and end up with -400 over here and a -10 delta D. Divide both sides by -10. Just regular math steps, right? And it gives you the same answer, right? Delta D equals the 40. And the same analysis, right? Oh, it's a positive, therefore, we're talking about positive forward and so on. So yeah, therefore from that one. So it's even working. Okay, so we just did displacement, directly from that. So again, everything's making sense. The VT graph work and the equation work is producing the same answers. And then finally here, like, what if we continued into the negative direction? I just want to give you an idea of, like, the kind of details that you might miss if you're not doing VT graphs, right? So we know that it comes to a stop after 4 seconds. And so I'm extending this and saying, okay, well, what if we went for like 6 seconds? Obviously, we're going to end up going backwards for a while, right? And so we did this one with the V2 is obviously the same as before, so I'm just going to skip it. Just your acceleration equation, right? But the displacement equation, if you look at it, really you're going to have a positive triangle and a negative triangle, a forwards triangle and a backwards triangle, right? So that is important. We got to remember that that's going to be a negative area because it actually means backwards. So you've got a 1/2 of base times the height that we already did before. That's going to be your 40. And then we're going to have this triangle here where we have 1/2 of that extra 2 seconds. That's where that 2 is coming from. This was up to 4, and then we're ending at 6. That's an extra 2. Delta V, when we put it in, delta V has to go in as a negative number. Okay, so it's going to go in as -10. Because the V2 numbers, I guess there's the V2 work, right? To get a delta V directly. So it's -10. And so we have 1/2 of a 2, and so basically it's just 40 take away 10 gives us 30. Okay, so we end up where we're 30 meters forward. So in other words, we haven't backtracked into the negative direction yet. The delta D, or the triangle, the equation version, sorry, equation version, we'd be able to use that equation and it would give us that same value. Again, we would have just picked the equation based on what variables we have and so on. So I hope that's starting to make sense to you. I'm going to, well, there'll be a homework page there. I haven't made it yet, but it'll be there when I post this up for you. All right, so if you have any questions, don't be shy. Email me, post a help thing, ask for a synchronous session if you want. I have lots of help available. Okay. All right. Till next time. Take it easy.